Hello, my name is Kuldeep, and I'm going to give you just a brief idea about how symmetric waveguides works. So, we start with the model builder section and just choose this parameter one. So, in this, what we are doing, we are just defining the basic essential parameters for the working of this waveguide. So, uh, in this parameter, uh, I define this operating wavelength which is equals to 1550 nanometer, and cladding and N core which is equals to effective indices of core and cladding. H core and H cladding are the thickness of this uh, core and cladding region. So after doing that, after defining this parameter, we go for this geometry in which we are defining uh, some layout of the our waveguide. So as we are working on some rectangular waveguides, so we just choose rectangles and we just choosing from this rectangles section. So we go start with this defining for the core region first, and then go for cladding region. So we start with the micrometer length. We need to choose this from this option. Then okay, then this rectangle one, this is which is corresponding to your core region. So I put this H core, which is the height of the core. W slab equals to width of the rectangle or rectangular waveguide, which throughoutly constant in this experiment. And in the base section, we put this as a center. And as we are working on a symmetric waveguide, both x and y coordinate must be equal to 0 for making this um, asymmetric. Just we need to do this, just move this y coordinate up and down depending on your working area. And now as we define core, we go for the cladding. Similarly, go for this cladding, as we need to replace it by h cladding. H cladding must be equals to must be greater than equals to greater than core thickness. So as we define the material layout of this waveguide, we need to define what kind of material it is made up of. So we go for this material section in which we choose the blank material for core and cladding. So we start with core. So you can see the core region lies in this second domain. Choose it from here and put the value of this core and core value, which we already put in the parameter section. So this defines the value of the refractive index of the region of this core, which is isometric and homogeneous throughout this experiment. In this cladding, then we go for the cladding region. Cladding region falls in this first and third, but second region is overridden, which is done by COMSOL by default, because as we already defined the second region, so there is no chance to define again it. So we have now we just define the layout of this waveguide. So now we go into this Maxwell equation. So we need to solve the Maxwell equation in the three region, in which in the cladding region it must go decreasing exponentially, and in the core region it must be sinusoidally. So these things we need to care of using this electromagnetic option. So like we need to solve this 1 2 3 in this both three region. So just we already put this three area of interest or area of interest 1 2 3, and we are working on the transverse electric field. So we just choose this out of the plane vector out of this three, and then we need to define our input excitation a, input excitation boundaries. So this is work as a boundary for the input excitation, so these you can see the arrow. This arrow is corresponding to this 1 3 and 5 boundary. So we define this boundary as an input excitation, input excitation. Then we define the port name, and the type of port must be equals to numeric. So as this is a input port, so we made this wave excitation at this port must be on equals to on. So now we already find the input port and go for the output port. So output port correspond to these three boundaries 8, 9, 10. And now we define similarly for port 2 numeric for the type of the port is numerical as we are working on this unidirectional waveguide. So excitation at this port is must be off. So we define the input port and output port and go for this boundary mode analysis in which we are going to select how many number of modes we have to work on. So how it goes. So we choose this as an effective mode, and this is from this is defined for the mode 1 for the first port. So we put this port 1 mode analysis must be equal to f node, and here is the game we are more interested in. So number of modes, desired number of modes in which we are working. So I just choose it at 1, which is equals to fundamental modes. So we will changing depending on the situation as we are moving further. So search for more around is meant for like we are interested in the searching of the modes in only core region. We are not interested in cladding region because area of working where most of the energy must be confined in the core region also. So in both analysis, this must be equals to n of core. So we are this, emphasizing this. So in the boundary modes analysis second, the same thing we need is only just we change the port name. So after doing this, we define this global OD, which we have just put this transcendental equation and initial value, because this what COMSOL does this. COMSOL use this Newton-Raphson method, which solves iteratively, which requires some initial values, which is equal to which I already put k core by 2. So this equation, these are solved by this COMSOL, and these equation will help us in analyzing the if value of effective mode indices index and propagation constant beta. So we will see further. So as we already now we have just characterized this waveguide completely. So now we go for the analysis. So we go for this compute button. So now you just see that how the energy is confined in this core region as depending on the core value, number of modes of the core value. So and below you can see the propagation constant value also. So I will give you just idea what how does it go. So you can see the energy, this blue and red region define me the energy is these are some oscillating field which form the standing waves in this core region, and no energy is going in this cladding region because we are working on this as fundamental mode. So most of the energy is confined, which is efficient in our working. So we can work on this. So now we have just see the field value. Now just we need to feel this graph, linear graph also. So as it this graph is also evident that this the most of the energy is confined in this our core region. So here from this to this, you can see my cursor. This is the region of the our core region. So most of the energy is confined in this. So as we increase the mode, this graph would be more bell-like shape. Would be more like more broadening, and most of the energy is uh, dissipate fall in this after this region of where core is not present. So uh, now we have just see the graph. Now we need to calculate the value equal. So in global equation, in the global evaluation, these are the columns in which different parameters of this Maxwell equation as we solved in the class will fall. So in global equation 3, I put this beta 1 and in an effective in which I am interested. You can see in global 2 here is alpha, which gives the solution of the transcendental equation. in equation 5, it gives you the propagation constant, overall propagation constant. But we are interested in this global equation 3. So you can choose many expression in this, and COMSOL, after solving this COMSOL, solving these value by COMSOL will put this value in the table section, and you can arrange it from. So I arranged it in these value in the table number 2, and in table number 1, some more value like refractive, these refractance and transmittance are putting are we are putting by this COMSOL. So I am interested in only these two values. So in every iteration after iteration, we have to click on this evaluate button. So evaluate option. So this will give you, like, you can see propagation constant is 5.99 and 1.47 is effective mode index. So as we further increasing the mode increase value, this propagation constant value and effective mode index will goes decreasing. Okay, so I will show you. Let's see. So I'm just slightly increasing the propagation value. Yeah, this mode, the number of modes, desired number of modes. So most of the energy will leak out as we increase just the number of, which is expected also. So let's see, and the beta value also decrease as we just find slightly increase. So now you can see some energy is leaking out this in this cladding region, which is expected, and you can now you can see also the graph also. So you can see then as number of modes and some slight energy, this you can see that the slight energy, some energy is now getting involved in this cladding region, the part of this cladding region. So now we calculate the beta for this mode. So as we click by on this global evaluation 3 and then evaluate this, so it will evaluate the beta and effective index. So you can see, earlier it was 5.99, now it becomes 5.95 and 1.46. Earlier it was 1.47. So this effective index value also decreasing. So now, like, uh, I'm increasing again number of modes. Like, let's go to 6. So it will take some time as we just increase the number of modes. So you can see it from this memory uses. So it is using the memory till 2 GB. As you can see, using memory is increasing. So it will take slightly time. As you can see that most of the energy now leaking out from this core region, which is inefficient transmission. So this must be take care of it. And now you can see, yeah, so I will show you this. As you can see, the most of the energy, like in this is the region of cladding, and in this region, the uh, wave equation must follow exponentially decay path, but it is now showing that is a slightly increase and decline. This is showing the sinusoidal path, like oscillating path, which is undesired, and most of the energy is turning out in this uh, cladding region, which is inefficient. Now we are calculating the mode value by using the same procedure. So mode value for this 5.90 for this. Earlier it was 5.95. So huge amount of change you can see. So we have just analyzed the how this energy changing. So this is what how this symmetric waveguide works. So let me know if you have any doubt. So I will clear you. So thank you. Thank you.